Okay, good afternoon, class. Can you guys hear me?
Yes, sir.
Okay. Any questions before I start?
Sir, these recordings, I don't see you sending them, sir.
They should be on the cloud. Not sure you guys got access to that, or I need to go in and copy the links and send them to you guys.
Yes, sir. You gotta copy link to send to us.
All right, I'll make a note to do that and send all of them to you. Also, final exams. So there are 2 sessions. Let me bring up calendar here. So the first session, I believe, is from the 12th to the 17th, right? That's 1 week of exams. And then there's another one in January, just after New Year's. Which one would you guys prefer to have the exam in? This one earlier, the 12th to 17th, or the one in January?
January, sir.
January?
Yes, sir. January.
All right, sounds unanimous. So I'll tell Mr. Jomo in January. Okay, good. So, I'm sorry, what was that?
Will it be online?
Well, no, it'll be in person. Also, do you guys know how the grading system works? The one with like in-person exams?
No, sir.
Okay, because I guess you guys would have, started university during COVID, so probably pretty much accustomed to online classes mostly and not really doing in-person exams. Okay, so the way it was before is that you would have continuous assessment course. So continuous assessment, right? And essentially you'd be given different assignments like assignment 1, assignment 2, maybe a quiz and a test, and then maybe a project, right? And these would, have certain weightings. Maybe this would be like a 10%, there's another 10%, right? There's like 5, maybe like a 30 and like a 20, and they would add up to about 100% of your grade, right? Now, the coursework plus final exam way that we're doing it now, this is actually the way, university would always operate. It's just that during this COVID period with online classes, most courses switch from this coursework plus final exam way of grading to this continuous assessment way of grading, right? Now, there are a lot of courses that, use continuous assessment, right, to be graded, but they're usually like maybe management courses that have a lot of coursework, a lot of like group projects, teamwork, team building kind of stuff. But courses that are like hard theory, usually you have like this coursework plus final exam way of grading. How this works is the coursework and the final exam are split up into two sections, right? So your coursework is worth 40% of your grade, and your final exam is worth 60% of your grade, right? And that there adds up to your 100%, right? And of course, an A is over 75%, and like a B, right, is over 65, and a C, so on and so forth, right? For your different grades. So all these little assignments and essays that I was giving you. So I give you an essay, right? So essay 1, and then I give you, I think, like a worksheet, right? You can call it a worksheet 1, as well as a project, right? Like a small project. All of this, they're termed coursework, and will add up to 40% of your grade, right? Now, the final exam, which is what you'll be doing in January, adds up to 60% of your grade, and it's just one exam, right? So as you can see, this final exam is a big part of your grade. Now, there are different courses that adjust this weighting a little bit, right? It might be 50, depending on the course, right? But the general weighting is 40% for coursework and 60% for the final exam. All right, so the exam is something, you know, really important, and you got to pass it in order to pass this course, I would say, or in order to get a good grade in this course. Right? And the coursework is there to kind of like help your grade. So let's say, you know, your assignments, your essay, your project, you do really good and you score like 38% out of this 40%. Well, even if you do kind of bad in the exam, let's say you barely pass the exam with like, you know, 50% of the exam, which would give you like a 30% overall out of that 60%, you still might get an A because, or you still might get a B, right? Because that's just 68%. So you can still get a B just because your coursework was so well, even though you barely managed to pass the exam, right? And as you can see, if you did something a little bit better, maybe you got like a little bit over half of the exam, right? You get something like 37%, you know, or 38%, right? Then you can see how easy it is to get an A, right? You don't have to get every single thing right on the exam to get an A, right? Because your coursework can help you. As well as if you do really bad in your coursework, right? Let's say you get something like 21% in your coursework because you did really bad, you can still get an A because if you get everything right, that 21%, plus let's say you do really good in the exam, let's say you do 65%, sorry, not 65, 55% in the exam, right? Then that still is like 76%, which is you can still get an A if you do really good in the final exam, right? So it's set up in such a way where you need to do good in both in order to get a good grade. But if you do bad in one, you know, the coursework can help bring you up. If you do bad in the coursework, the final exam can help bring you back up to a good grade. Make sense? You guys understand the grading system, how it works?
Yes, sir.
Good. So any other courses you guys got final exams for? I'm sure a lot of them would have switched over
All
to
of them, sir.
All them, sir, all.
Okay, good. So the final exam is super important. Make sure you study fit. Don't fail it, right? It's 6% of your grade, right? And also coursework is super important. So, and coursework is really easy to get grades in, right? So if you just, you know, write that essay, do that project, do that assignment, that's like 3 marks, right? That can help you if you manage to miss a question or two in the final exam. You can still get an A because your coursework is so high, right? Okay. So that project that you guys owe me and the, you know, the worksheet, all those come towards your grade, right? Yeah. So let's start off with a little warm up, right? Let's work this example. Now first, white out the answer as usual, and you guys can take a look at it. And then tell me what you think the answer is. So what this system is a BCD decimal decoder, right? It accepts a binary coded decimal input, right, the BCD input, and activates one of 10 possible decimal digit indicators, right? So, of course, you would have some sort of understanding of this work. When the BCD number, let's say for 8, which is 1000, comes into the inputs, right? The decimal equivalent, the switch for the number 8 is going to become active, right? So this 8 would become active. And how it becomes active, remember there's this little circle here, and that circle means that it's an active low. This would become active by displaying a low pulse. So that would be 0 volts, right? Plus 0 volts. And everything else would be high, right? So you would have a 1 here, 4, 5 volts, right? So you'd have 1 straight throughout here, and you'd have your low at the gate 8, right? And a 1 everywhere else, because this is an active low decoder, right? And we know it's an active low because of these little circles there, right? Same circle you find at the end of a NAND gate or a NOR gate. So for this example, the inputs of this chip, 748C42, are the sequence, this input, right? Which is of course a BCD input, this and this. So it wants you to now describe the output. So looking at these inputs, what are the outputs going to look like? Take a few minutes and see if you can figure it out, right?
Sir, so the outputs, right? When you said describe the output, we're just saying like which numbers are gonna show up on the display or something?
No, how the outputs are gonna be. So let me just do the first one, right? So this first number here, that's 5 in BCD, right? So that's 5 in, well, BCD is just regular binary that doesn't go past 9, right?
Yeah,
So
when
that's
it's
5. So we know
decimal.
for 5, everything is going to be high. 5 is going to be low, and everything else is going to be high. So when they say describe the outputs, that's what they mean. So when the input is this number, what does the output look like? Well, the input's 5, so it's going to be 5 is low, and everything else is going to be high, right? You get it?
Alright, so the sequence is gonna be 5, 6, 3, and 2.
Yeah, as being low. 5, 6, 3, and 2. Yeah.
Okay, sir. And so this particular chip here, would it retain the previous input or would it just proceed on to the next?
No, so it just proceeds on to the next. So what happens is that this chip only responds to the inputs, right? So if the input is 0, 1, 0, 0, right? 0, 1, 0. 1, sorry, which is 5. 5 is going to be low and everything else is going to be high, right? Then when the input switches, let's say it switches to 0, 0, 0, then this is going to instantaneously switch to 0, 0, 0. So this one is going to be low and everything else is going to be high. It's going to switch as the input switches, right? It decodes whatever the input is. So whatever the input is, the output is going to be based on that, right?
Well, technically the inverted version of that.
Yeah,
Or
the
not. Yeah, it's the
because
inverted
this is an
because
active low, right? Yeah. Good. So active low. Okay, and it's also important to remember like none of these chips have memory in them, right? They just respond to the inputs and the outputs, right? If you don't put anything here, like nothing's gonna come up here, right? If you don't, these chips also, they come with like other pins, right? VCC and ground, right? So if VCC and ground are power and all of these are low, right? Then this one is going to be 0 and all of these are going to be high, right? All of these are going to be high because you're powering the VCC and the ground, right? They come with a data sheet and they're in that same dip packet we talked about earlier in the course, right? So you would, to power this chip, you would have to connect it up to some sort of power source, right? Okay. Now let's do a little bit of design. Not fully, but we're gonna try explaining it a little bit. Okay. Now let's talk about this chip. This here is a new chip, slightly different from the regular decoder. This is a BCD decoder and 7-segment display driver. What this does is and let me look at it from a systems view, is it takes an input, right? The input is BCD, binary coded decimal, which is just binary that goes up to 9, right? So let's just rewrite that binary that goes up to 9, right? Because it doesn't display the 10. And it output that as 7-segment code, or just powering the lines of 7-segment display. So we got 7-segment display like this. And the 7-segment display obviously has 7 segments, right? 1, 2, 3, 4, 5, 6, 7. Right? And then again, to light up particular number, we just light up the different segments. So let's say to light up the number 5, we would light up this segment, then that one, then that one, then that one, and display the number 5. So what this looks like is BCD comes in, and then the output is whether or not we want each of these 7 pins on. So let's define the inputs and outputs a little bit better. Obviously, it's not one single line coming in. You can maybe with serial input, but it might be a bit harder to design. And it's not one single line coming out. What's coming in is 4 lines, right? Because BCD is 4 bits, right? So, for example, the number 9 is 1001. And then what's coming out is whether or not each of these 7 segments are going to be lit up, right? So A, B, C, D, E, F, G, right? So 7 data points are going to come up. 1, 2, 3, 4, 5, 6, 7. So for the number 9, right? For the number 9, it's going to be inputted here, right? 1001. And what's going to happen internally is we're going to do some decoding, right? And maybe some encoding as well, right? So we're going to decode this there to the number 9, right? And then have something called an encoder. And it's going to convert from number 9 and say, hey, you know, light up a particular set of pins. So we know to display the number 9, and let me do this in green, we're going to need to light up A, B, D, C, G, and F, essentially everything but E, right? So all of these pins are going to be high except the E pin, right? So that's what the output is going to look like. And of course, I'll go over how we design the encoder in a few slides, right? But that's essentially what this chip does. Okay.
So in the case of this active low, right? Like for example, it wanted for this 35, right? So those two segments, those got the 5 low output would have got take off them to LEDs, basically, or those 2 segments, while the high is them bring on the remaining segments.
Yeah.
Okay.
Yeah, it would turn off this one and this one, and this one would be high, this one would be high, right? And
So
different
what's
chips
the advantage over the active low and the active high?
Depends on it's just how you design your circuits. So I don't know if you read chapter 5, but there's a part in there that's kind of useful. What it says is that every single gate can be made using a NAND gate or a NOR gate. Okay, so let me open up chapter 5 real quick. So every single gate can be made using a NAND gate or a NOR gate. Now there's a slide that displays that specifically, right? So, and let me know, can you guys still see the screen that says universal NAND gates?
Yes, sir.
Yes, sir.
Good. So let's say we wanted a NOT gate or an inverter. If we took a NAND gate and we wired it up like this, it would be an inverter, right? Right? Then you can think about it, but when this is 0, right? The output is going to be A bar, right? If we think about A and it with itself, and then barred, then what this really works out to is just A bar, right? You can think about it a little bit, but essentially that's what's happening here, right? So like A is 0, right? Here is going to be 0. Here is going to be 0, right? The NAND gate is going to output a 1 when all of its inputs are 0, right? When this is 1, here is going to be 1, here is going to be 1. When all of its input are 1s, it's going to output a 0, right? So it's going to operate like a NOT gate, right? It's going to operate like the inverter. Now, an AND gate, let's say we want to make an AND gate from a NAND gate, right? What we do is just take the NAND gate here and just send that through a NOT gate, right? Because we know if we took 0, we send it through a NOT gate, it becomes 1, and we send it through another NOT gate, right? It just comes back 0. So if a NAND gate is an AND gate, right, plus a NOT gate, if we send that back through another NOT gate, what we end up with is just an AND gate, right? And now you can take your own time and look at the other ones, but this configuration, and you can work through it, this configuration here actually gives you the same output as an OR gate, right? And you can do it Boolean algebra wise, or you can, draw your little sections and do it in segments and use the different possibilities, the different inputs. But trust me, this works out to an OR gate. And this here, as complicated as this is, because this section here is just an OR gate, sent through a NOT gate turns into an OR gate. And you can do this for all the gates. Now, it just so happens that, when building logic, it's easier to manufacture this thing by just manufacturing one type of gate. So if you're trying to build logic gates or print logic gates onto a silicone wafer, it's super easy to just print a million NAND gates than to print one NAND gate, one OR gate, and all these different fancy configurations. Just print a bunch of NAND gates and then wire them up accordingly, right? So because of this, it really helps simplify the manufacturing process. And since we're going to build everything from NAND gates anyway, right? Sometimes it's easier to have active low circuits. Does that kind of make sense?
Sorry, yeah, makes sense.
Yeah. All right, so that's where active lows work. And they probably got some other reasons too as well. So you can do your little research on the side. All right, so that's what this chip does. Okay, now there are two other parts, right? Which is the ripple blanking input. And of course, when you look at this chip, right, you see the VCC and the ground. Of course, it's not going to be like this in the actual chip. The actual chip is only going to have pins on either side. And maybe this one might be VCC and this one might be ground. Right? And your data sheet is going to tell you all that and tell you how to wire everything up. All right. So let's talk a little bit about these other inputs here. Right. So this here just showing like, the inputs and lining it up to the 7-segment display. Of course, this is the LED. So we know when we got a battery source, right? We always put a current limiting resistor, right? We always put this current limiting resistor in order to not blow the LED, right? So if we just put a battery and the LED, this LED might, short circuit, might blow, might got too much current going to it, right? So we usually put a resistor in line with it. And the resistor could be anything from 220 ohms to 1K. And it's just dependent on the LED. So your LEDs, like this 7-segment display, will also have a particular data sheet, right? With, running currents and all these things in it, that you can use simple things like Ohm's law to help calculate what this resistance should be. Okay. But usually we just take a small resistor, we might have like a little cup with a bunch of little different size resistors, and we just might take something within the range of 220 ohms to 1 kilo ohm, just slot that in there. Right? Because those generally work. All right, good. So now we're trying to build something. Okay, and we're using this chip because it has a particular capability that we like, right? It's able to drive 7-segment displays. And we've built the rest of our circuitry to break down our numbers. So after we do the addition, the subtraction, whatever sort of processing, we ended up with numbers like BCD for 90. So BCD for 90 would be 1001, which is the number 9. Right? And this would go to one 7-segment display. And remember, the number is 90, so they would have another BCD number, which is just 000, which would go to the other 7-segment display. So like, let's say we have a row with 4, 5, 6, 7 7-segment display. One is going to display 9, and the other is going to display the 0, showing up the number 90, right? So you can start to see how different things like calculators, simple computers, your microwave display might work. Right? Good. So we got this thing lining up, right? And here is coming the input 3, right? 0, 0, 1, 1. And that there is translated to this 7-segment display, which says light up this segment, this, and this, and keep this one off and this one off. Right? And for 0, right? 0 is the input coming here. It says light up these ones, the ones around, and keep this middle one off. Right? This one, it was on, but this one, it was off. Right? That's how the chip works. Now,
That is overkill, sir.
I'm sorry, what was that?
I said a circuit is overkill. Stringing all those drivers together.
Yeah. So now the reason we string all of them together is so that we can save some power, right? So what you would notice is that these are 0, but this doesn't light up as 0, right? The 0 doesn't light up here and the 0 doesn't light up here. That's because the circuit is talking to each other via these inputs and outputs, the ripple blanking input and the ripple blanking output, right? Ripple blanking input, ripple blanking output. And this allows us to do a very simple thing, which only lights up the significant digits, right? The digits that have value. So let's say we were, just doing a number 0030, like a regular decimal number, a regular base 10 number. That's just 30, right? We don't actually write the zeros in front of it. So when we might be displaying a number on a calculator or something like that, right? We don't want to write 00000 like on all the displays and then write your 30 on the 2 last displays, right? Of your LCD or your 7-segment, grouping, right? We want everything else to just be blanked off. We want this to be blanked and this to be blanked and just the 30 to be displayed. Right? So at first you might think, okay, easy. If the input is 0, right, turn it off. But what happens, right? In situations like 30, the input is 0. We don't want this turned off. We want this on. So we need communication between the different chips. How we do that is we start by saying, okay, the ripple blanking input is 0. If the ripple blanking input is 0 and all of the other inputs, the BCD inputs, are also 0, then blank the display, right? And the output for that display is going to be 0, right? The ripple blanking output is going to feed it forward, cascade into the other side of the circuit as a 0, right? So we start off, right? This is just a starter with a 0 input. And the logic is set up so that if this ripple blanking input is 0 and all the BCD inputs is 0, then blank the circuit off. And then feed it forward, right? Okay. Yeah. So now we're feeding it forward, and this one here, the ripple blanking input is 0 because it was fed forward on the last one, and all the other inputs are 0. So this one is blank, and feed it forward, right? So the ripple blanking output of this one is going to be 0, and that's going to be fed into the input of this one, which is 0, right? So this is 0, but the BCD input is non-zero. So therefore, this is not blank, and it displays the number. No, this is not blank. Therefore, the ripple blanking output is going to be 1, which is going to feed into the ripple blanking input of the next 7-segment display, right? The next driver, which is 1. So even though this one, the BCD input is 0, the ripple blanking input is non-zero, it's a 1. So therefore, this 0 is displayed. That's how this chip tells this chip, hey, this number is significant. It wasn't blanked out. It's non-zero. So therefore, this 0 needs to be displayed. So you can see how this would be useful in certain situations. And we obviously wouldn't want to waste power because wasting power is battery life. Right? And you don't want to have a computer that just, or a calculator that just runs out of battery all the time, right? Okay, makes sense? Any questions? No questions? All right, moving on. So that's leading zeros, right? Now trailing zeros is suppression. So let me give you guys another scenario. Let's say we had a number like 7.625, right? 0.0006. This, for a number like this, these zeros you actually want to display. But let's say for a number like 7.62000, and the zeros just keep going on, filling up all the 7-segment displays. These zeros don't actually mean anything, and you might choose to not display them. Only display the digits that matter. So for the trailing zeros, we have a similar setup, right? But it's just wired feeding forward, well, cascading from right to left instead of from left to right. So instead, in the previous one, right, we cascaded from left to right. This one, we're going to cascade from right to left, right? And it does the same thing, just to chop off all the zeros, right? So the ripple blanking input again, 0. Here is 0. This is blank, and it's fed forward from the output of this chip to the input of the succeeding chip, right? So the ripple blanking input here is going to be 0. This is going to be 0. So the output is blank. This ripple blanking output of this chip is going to be fed forward into the ripple blanking input of this chip, this following chip, and tell it, hey, it's 0. But since the BCD input is non-zero, it's going to actually display the number, right? So that's all this method is. Just the modification of the previous one using the same thing. It's just the chips are, lined up from or fed forward from right to left instead of left to right. Okay. Make sense? Any questions?
Sir, so with these chips, right? Technically you're not given an output, you're just syncing the voltage from the 7-segment display to ground because this is octave low, which means you gotta use common cathode displays, I think. Is that correct?
Yeah, so there are different types of 7-segment displays, common cathode, common anode. So it depends on your circuit, right? And it depends on what this chip does, right? So this chip, even though it has like active low inputs, it might be designed for a common cathode setup. So you can actually like take all of these inputs and put NOT gates through them and have the reverse effect or something of the sort.
Oh, I got you.
Yeah, so it's up to you on what kind of 7-segment display you want to pick, but yeah, you can use common anode, I think.
Yeah, with common anode, you're gonna have to invert the inputs.
Yeah. And what I always recommend is to test it first, like test it, see if it doesn't work, and then, maybe you can wire some things differently, right? Yeah. And that's also why multi-sim is useful, right? You take a chip, you type it in, and then you simulate first, and then you build. Okay. Okay. So as promised, the encoder. Now an encoder is fairly simple, right? Let's say we wanted to press a button, like press a button for 1 and have that display the number 1. And we're using maybe BCD, right? So the BCD number for 1 is, let's use A0, A1, A2, A3. That would be 1. Oh, sorry, it's actually the other way. So A3 is the last one. That's the most significant bit. A2, A1, A0. For 1, A0 would be high, and all the rest would be 0. So how we do that is just by using a series of OR gates, and we say, hey, for whichever one that requires that one to be turned on, just feed it into the OR gate. So for a number like 1, it's just fed straight into the OR gate, and then it's omitted from the other OR gate. So this alone would turn on, right? Now for something like 2, right, which is 1, 0, that would only be fed into A1's OR gate. So it'll be fed only into A1's OR gate, and is going to be omitted from everything else. For something that requires multiple bits to be on, for example, 7, that's going to be fed into all the different outputs via their OR gates that needs to be turned on, right? So we know for something like 7, it's 0, 1, 1, 1, 3 ones. So it's going to be fed into this one, A0, this one, A1, and this one, A2, but not A3, right? As you can see, it doesn't go to A3. And that's simply how a decoder works. Let's put this into a little bit more context. When we think of a number pad, right? A little keypad. So you got keypad. Let me find one like a Google image. So you got keypad, right? This is very common one in electronics, right? And you press the different button, and those different buttons are essentially just pressing switches, right? So you would press your switches, whether it be 0, it'd be 9, it'd be 7, 6, whatever it is. And a little resistance along different parts of the line, and you got your VCC and your ground so that electricity can flow. And your switches essentially connect up different circuits and send signals, right? So you got your VCC coming in, right? And then you close this switch. What that does is create a path to ground. Creates a path to ground. So this input at 9 is actually going to start showing low, right? It's going to be 0. Let me explain why. So previously, VCC, let's say it's 5 volts, would be flowing. And what this would be seeing is actually a high, right? But when we close this, we establish a path to ground, changing this to low, right? Because electricity is going to flow through the path of least resistance, right? It's not going to go through the chip. It's just going to go straight to ground. So here, instead of being high, it's going to end up being low. And now since this is an active low chip, when here is low, that means this here is activated, right? So this here is going to be lit up. Going to be activated. So now when we think back of a circuit like this, and you see that 9 comes in active, then we know 8-3, right? Let me use the other one. This one has a lot of red marks on it. Right? Let's say 9 comes in active, then here would light up and give us the 1. And here would light up and give us the other 1. And all the other would be 0, right? Now, of course, you switch it accordingly, and the data sheet is going to tell you how exactly these numbers are going to come out. Instead of coming out 1, 0, 0, maybe the chip being active low or active high might actually come out 0, 1, 1. And you might need an inverter setup here or an inverter chip to just flip that to the right way to be compatible with the next series of chips or the next part of your system. Okay? So does that kind of make sense how this would work? Press a button, right? You press 9, that sends the signal, the trigger, right? The active low, the active high, right? However you want to set it up, right? This here could be the ground, and this here could be the VCC, right? Yeah. And that just says, okay, whichever pin is active, right? And that decides what the BCD output is going to be. So inside this chip, when we think about it, it's really just a connection of different OR gates, right? It's really just something like this. Very simple. 4 OR gates, 4 bits, super simple. Of course, you know, a little bit of supporting things inside, like maybe a resistor here and there, some pull downs, some pull ups. And the actual OR gates are built off of transistors, or they might even go a step further. And each OR gate might just be NAND logic, right? Each of the OR gates might just be a series of NOR gates. or a series of NAND gates. So that might complicate the logic. So when you take something like this, that's four gates, and then you convert it using NAND logic. The actual amount of gates you might need is 3 per gate, which might be 12. Okay? But it pays off, even though you're using more gates, because remember the manufacturing process, you're just manufacturing one type of gate, right? Hundreds, millions, billions of them, and putting them on a single chip, connecting them up in a particular way. Okay. Okay. So I want you guys to take a few minutes and do this example. Just kind of think it through and work it out in your head or on some paper if you got that available, right? So think of this input going through this system. Think of what the outputs are going to be, right? And then think of those outputs as the inputs to this system. And think of what their outputs are going to be, right? And then compare the inputs to the output and tell me whether or not this setup does what it says it's supposed to do, right? These here are two examples of a 4-bit binary to gray code converter and a gray code to binary converter. Right? Also, you can refer back to chapter 2, which has like that gray code table that might help you, convert easily between the two, because I don't even know how to like count in gray code, right? So
Sorry, they got
maybe it might be
a
helpful.
format for it, sir.
Yeah.
The same particular logic gate system here is showing the format. Where you take the like say you got bit 0, you XOR it with bit 2, and you take bit 2, XOR it with bit 3, and so on, and you leave the MSB as the same,
Mhm.
and you get your code.
Yeah. I usually just count. Like I would look at it. So I would do like 0, 0, 0, then 0, 0, 1. Then think about, okay, I need to go higher, but I can only change one bit. So for here, I do 0, 1, 1. Kind of just think it through. And I know here, okay, I missed 0, 1, 0. So for this one, I'm going to do 0, 1, 0. And then so on and so forth. Yeah, but using this logic gate, this converter, it's easy to develop the pattern. All right. So do the exercise, do the example, verify that this circuit works, and let me know if you get lost along the way or have any questions. Okay, all finished?
Yes, sir.
Okay, so let's look at the outputs. Okay. And you can use a quick reference table. You can usually find quick reference tables by just Googling them. So you can do gray code to binary. And there's almost always a Google image that would have that stuff available really easily, right? So you can use that to check certain conversions. There might also be, you know, just the BCD table, which gives you binary coded decimal. It's a decimal number in the BCD. So you can always just Google a quick reference table if you ever needed to compare them. But I'll trust this slide and I trust that everything is right and everything is on the up and up. So what this first circuit would do is convert the binary to the gray code. So as we can see here, it XORs these two. And remember, XOR is the exclusive OR, right? It's like an OR gate where either of the inputs need to be high for it to be high, but it's exclusive in the sense that if both of them are high, then the output's 0, right? So how the truth table for that XOR gate would look is like 0, 0, the output 0, 1, 0, the output's 1, 0, 1, the output's 1. But unlike the OR gate where both of the inputs are high, the output's high, this one here excludes this one, makes that one 0, right? That's all. And as you work through this circuit, you'll find out 1, 1, 1, 0 translates to 0, 0, 1, 0. Did everyone get this? Anyone, you know, had
Yes, sir.
trouble?
Yes, sir.
Okay. Good. And then we put this back into the converter that does the reverse, that converts gray to binary. Right? You put it through, use the XOR gate inputs, right? Notice that the second input for this first XOR gate is fed from the output of the XOR gate below it. And they're all kind of fed that way. So it's kind of like we start with this one, follow straight through, feed into the XOR gate, XOR with the other one, and then the output of this stage is fed into the next stage, and so on and so forth. Right? So we take the truth table of the XOR gate, we look at this, and the output we get here should be the same as the input we started with. And that's a quick way how we test that this circuit here works. Now, this circuit might seem as if it appeared out of you, but you can actually develop it by going through a really long and arduous process, right? First, we would do is get one of those reference gray code tables. Right? You would start up, maybe you might start a bit smaller, right? You might start with like 3. So you look at all the binary numbers for 3 different inputs, right? So you look at 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on and so forth, all the different possible inputs, right? Then you create a table with the gray code outputs. So it would be like something like G1, G2, G3, right? And then you would say, okay, for 0, 0, 0, what's the gray code, right? And it might be XXX, and so on and so forth, right? Populating the gray code here. And then as we know, G1, we might need a kernel map or Boolean algebra exercise to develop the gates. And then for G2, again, we might need a kernel map Boolean algebra exercise to develop the gate. And then through simplification, you know, applying your kernel map techniques, applying your Boolean algebraic techniques, and just visual inspection, you might be able to group certain circuits together, certain things together, and then end up with this much simpler circuit, right? But of course, it's a process to get here, right? And that process requires you to use all the techniques that you've learned, right? So let's move on. Now, multiplexers. Again, another functional block we talked about in the first class, right? We say multiplexers allow us to send or multiplex data from multiple sources over a single line, right? So we got data coming from data source 1, 2, 3, and 4, right? 4 different data sources. And we multiplex those all over the single line, right? So for a certain time, let's say T1, we're going to have data coming from D0, line D0. And for a certain other, time period, let's say T2, we're going to have data coming from another line, right? Now, how the multiplexer operates, it's by taking data select inputs, which helps establish the rhythm of how this multiplexer switches through line. So naturally, we would expect that the multiplexer for some time period, right? Let's say delta T, maybe that's 1 second. For 1 second is going to connect to 0 and transmit the zeros and ones associated with these 0. For the other second is going to connect to D1 and transmit the zeros and ones associated with D1. And then so on and so forth. And then roundabout, like go back to 0 and there for 1 second, connect up to D0, let that transmit, let those two systems connect, and then go back to D1 and D2. So you might be in a situation where you got system 1, system 2, system 3, all want to be connected to the master system. And you got this one talking for like 1 second. Then it's going to switch over and talk to this one for another second. And it's going to switch over and talk to this one for another second, right? The data is being multiplexed over the same line, right? Time shared. Now, how the data select lines come in is that this 1 second isn't just something we go in and we say, hey, multiplexer multiplex by 1 second. We need to actually send a signal with that timing telling, the multiplexer to switch. So in this data select line is where that timing comes in. So you might have some sort of two output counter here telling the multiplexer, say, hey, okay, 0, 0, connect up to D0. 0, 1, connect up to D1. 1, 0, connect up to D2. 1, 1, connect up to D3, right? These numbers might be familiar because they're just binary numbers, right? This is 0 in binary. This is 1 in binary. This is 2 in binary, and this is 3. That's essentially what these data select lines do to establish the period of oscillation of this multiplexer, right? The period at which it switches between each of the different lines, right? So when it sends a 0 in, it's going to connect up the data line 0, the 1, the 2, the 3. That's which line is going to connect in. Now, as we know, counters have a certain frequency to them, right? So you might have two signals coming in, right? It's going to be 0, 0. Then it's going to be 1, 0, right? Then it's going to be 1, 1. Sorry. Then it's going to be 0, sorry, 1, 0. Then it's going to be 1, 1, right? And this here is going to have a certain frequency associated with it, right? So this is 0, 0 here. Let me put in red. This here is 0, 0. This here is your 1, 0. Right? This here is your, sorry, this is your 0, 1. And this here is your 1, 0. And then this here is your 1, 1, right? And then there's a certain frequency certain periods or certain delta t associated with this, with how fast these signals change, right? And how it switches through the different data select inputs, right? So this here, in terms of binary numbers, would just be 0. This here would just be 1. This here would just be 2. And this here would just be 3, right? Just switching through it with a certain frequency. And that's how it selects which line is talking to or having its data being outputted at a certain time. Of course, you don't have to set it up in an oscillating fashion. You can, set it up in a totally manual process or a totally dependent process where you press some switch and that switch sends the input 0, 1, and that system is connected to 0, 1 is, so S0, S1, that's 1, 0, which is binary 2, which says, hey, connect up the data input 2, and that one is having its data outputted, right? You might have some switch that just sets it up this way, and then another switch that sets it up to data line 3, and this switch or this input signal might be dependent on some other circuitry, right? Might be dependent on getting a request to communicate, right? So it could be that, some sort of master system here is communicating back to your digital system, right? And it says, hey, I would like to speak to system 0 or system 1, and that feeds into your data select lines. And decides which line is connected up to the output, right? Could be just that this system over here, it's fed all the way back into this data select line, right? Totally dependent on your system, totally dependent on your application, different purposes. Any questions on the multiplexer? No. Okay. Now, a demultiplexer. Now, this demultiplexer, originally we introduced this chip as a decoder, but the decoder can actually be used as a multiplexer, right? So originally as a decoder, let me write decoder here. When we looked at this chip, we looked at something like 0, 0, 0. That's gonna make this low and everything else high. We looked at 1, 0, 0, which is gonna make this low and everything else high, right? Because active low, right? Essentially just decoding the number that comes in. But we can actually use this method of operation for a demultiplexer. Let's think that through, right? Right, so a demultiplexer has one data input coming in, right? Let's say this is the data input coming in. And that's just a stream of data, right? So in here comes a stream of data. And the data select line says, hey, make this line active or this line active or this line active. So let's say we put a number like 7 in, which is 1, 1, 1. That would make this line active, right? This would be 0 and everything else would be high. But this line here would be active. Or if we did something like 3, which is 1, 1, 0, then this line would be active. And you remember this these here, this enable inputs, which turn things on and off, right? So remember, for the active high ones, we need to send the 5 volts here, or we need to send a 1 in, a high in, or else the chip would be off. And for the active low ones, we needed to send the low in, or the chip would be off. Turns out, if we just send data through it, like we just send a string of 1s and 0s, this chip would be turning on and off, right? Depending on what the input in is, right? So let's say we use the data select line to say, okay, this data output 3 is active, right? So it's going to be active all the time. We just select this one, it's going to be active all the time, right? Then we say, okay, now based on this input, which is the actual stream of data, turn yourself as the chip, turn on and off based on this data. So all that's going to be happening is the output here is going to be recreating data coming in, because this enable pin needs to be 1 for the chip to be 1. If it's 0, the chip is going to turn off, right? And this data here is going to be cycling through based on the output of this. And then with that, you might want to do some playing around, maybe, right? So you want to select the chip and maybe use an active low input or active high input based on whether or not you want this to be the exact replica of this, or if you want it to be an inverted output of this, right? All depends. Does that make sense? How we would select a line, turn it off, turn it on, make it active, right? Having it high all the time, and then using the enable inputs to cycle the chip on and off, right? Cycle the chip on and off, turning on and off, essentially replicating the data output. Any questions? No. Okay. Okay. I'll leave this one for you guys to do as homework. And we move on to parity generators / parity checkers. Okay. So we talked about even and odd parity a little bit earlier in the course. And we know it's a error detection method, right? That just uses an extra bit which we append to the data. And then as we send the data through the system, we can always go back and check. Now, let's look at this example real quickly. So they ask you for the letter S. It's sent using this. Now, if we want to send that data with odd parity, then we, of course, first we got to count the number of ones. So 1, 1, 2, 1, 3, 1, 4 ones, right? We're using odd parity. Therefore, the number of ones in the data, in the section of data, be it a bit, byte, in the section of data, needs to be odd. So this, since this has 4 ones, we need to append another 1 to make the data odd, right? Make the data have odd parity, right? So with odd parity, we append a 1. So if the data is transmitted and we're checking it on the other side, and let's say one of these bits, one of these zeros accidentally got flipped and turned into a 1, we would count the number of ones, 1, 2, 3, 4, 5, 6, and we'd say, hey, the system is odd parity, but the number of ones I got was 6, something went wrong. Same way, if one of the ones turn into a 0 accidentally, we count the number of ones and say 1, 2, 3, 4, and say 4. The system is odd parity. Something went wrong. Right? Same thing with even parity, right? So we count the number of ones as 4. It's even parity, so the bit that we append to it must be 0. Okay. So now let's think about how we would build a parity checker. Right? Let me open up Paint. Let's think about how we would build a parity checker. And a good technique to start building these things is when you don't know how exactly you would go about doing them, it's good to start small. So let's first build a parity generator for maybe a 2-bit system, right? So we list all the different possibilities, right? One input. We shouldn't do AB. We should graduate a little bit and do A1 and A0. And the parity bit based on that, right? So there are 4 possible outcomes of these 2 bits, right? There's 0, 0, 0, 1, 1, 0, and 1, 1, right? And let's say we're doing odd parity, or maybe even designing for even parity. The output of this generator for odd parity here should be a 1, right? Because we want to make the number of ones odd. Here would be 0 because the number of ones are already odd. Here would be 0 because the number of ones are already odd. And here would be 1 because the number of ones are 1, 2, which is even. So we want to add a 1 to make it 3, which is an odd number of 1. Now from here, we can do the Carnot map, or we can do Boolean algebra, right? We can do something like A1 bar ANDed with A0 bar, or A1, A0, or develop your Carnot map and make your groups. Or you can say, hey, you know, this pattern kind of looks familiar. And you can go back to chapter 3 and scroll through and say, hey, maybe there's already a gate that does this, right? Maybe there's already a gate like the XNOR gate that has the same pattern. So when we want to build a parity generator for a 2-bit system, all that is an XNOR gate. Now, let me give you guys a chance to work it through and figure out what gate, if there is one, or what group of gates you can use for an even parity generator. All right, so take 5 minutes and figure out what you would put here and what gate you would use for an even parity generator.
Sorry, I'm gonna use the exclusive OR gate.
I don't know. Walk me through it. How did you come up with that? So and put in red. Even parity. Let's first build the truth table, right? For 0, 0, what's the even parity bit gonna be?
Sorry, not 0. Oh,
Good. An even number of ones, right?
yes, sir.
So for 0, 1, what's it gonna be?
We're gonna be 1 and then 0.
Okay, good. And then you look through what gate is that?
Exclusive OR, sir.
Okay, good. Easy, right? Now, what about the parity checker? How would you build the parity checker?
Sure, it'd basically be a circuit with basically 3 inputs, because you gotta look at your data bits that's coming in, and look at your parity bit that's coming in, and then check to see if the parity that you generate is equal to, well, you gotta, let's say equal, you gotta AND it with the parity bit value.
Okay. Let me give myself a little bit more space here. So something like this, yes, would be
Yes,
your
sir.
output.
Yes, sir. And well, if the output is 0, then it means that your parity, that means that you have some bit loss, some errors, and if it's 1, well, everything's good.
Okay, so are you sure this is an AND gate?
Um, thinking about it, it may as well be a XNOR.
Yeah, it needs to be a comparator, right? Right? It has to make sure these 2 bits are the same. And the XNOR is just a 2-bit comparator, right?
Yes, sir.
Okay, good. Because the bit you generate, whether it's 1 or 0, right, needs to be equal to the parity bit you received from the system. Okay. So that's just trying to teach you guys the principles, right? How do we actually go about building this? Of course, building a parity generator for 3 inputs might be a little bit more difficult than 4, 6, 8 inputs might be very cumbersome, might take a long time. But that's why you learn all these tools, right? That's why you learn the cardinal map. That's why you learn the Boolean algebra. That's why you got multisim to help you do the analysis. So maybe for your project, a good project idea might be something like a 6-bit parity generator checker combo. It might be a good project to build, right? And of course, you can be creative. Students build all sorts of things, and very creative, and the final project, the output is usually pretty good and pretty interesting. Okay, so be creative. All right, that's all I have for you guys for this slide. Chapter 7. It's really just something you can read. It's about storing data, different SR latches, different types. You can go through them nothing complicated to it. And in terms of the exam, it's now going to come as a really big part, a few multiple choice questions on it. All right. And that's it. That's all I have for you guys for the course. Any questions specifically for the course, to the exam, for your project?
Yes, sir. The exam. I can't really recall if you spoke about this, but what form would the exam usually take? Multiple choice and essay type, or essay type alone?
Yeah. So multiple choice. So probably mentioned this before. So you see, they're usually multiple choice questions at the end of the slides. Yeah, you guys get the slides with multiple choice questions at the end, right? They're like these, multiple choice questions. They're usually at the end of the slides. Right, so these questions are probably going to come back, maybe slightly different, right, in a different order, maybe grouping a couple of them together, maybe a few new ones they never seen before, but you're going to get like about 20 to 30 multiple choice questions. I'll try typing up an email summarizing the format of the final exam. You're going to get some, I wouldn't say essay type, but like essay / like short answer / working questions, like you're gonna add a binary number or explain how a floating point number is stored, right, in a digital system. Things like that. Maybe I give you a Boolean algebraic expression and actually tell you simplify this, or write it in a particular form. I might give you a cardinal map, right? I might just give you the map and say make groups, make the minimal POS for this. Things like that, right? I'm gonna ask you, give you a Boolean algebraic expression and be like, show me the combinational gate logic for this, like, how would you wire up this circuit, right? Give you a Boolean expression. Let me give an example of something real simple. Something like, A plus B, right? It's not going to be this simple, but you should know that that's just an OR gate, right? That's A and B going into an OR gate. Maybe I give you something like A bar B or A B, like, how would you draw this out, right? How would that look?
Or so you
I mean, but A.
don't have to simplify the expression. You just have to draw the logic network.
Yeah, but there will also be ones that come asking you to simplify them, right?
And draw the network.
Yeah.
Okay, sure.
And the cardinal map, like, make sure you know that for sure, because it's not going to be any way getting away from it. It's not going to be super difficult, but it's going to be, something you got to do to get some points there.
Sir,
So
there's only one unique solution for minimizing POS and SOP, right?
so there are multiple solutions, but when it's minimal, like the minimal solution, there's usually just one.
Okay.
So the way to get the minimal solution is by making larger groups. Remember, we went through the whole process of making group 8 or making group of 4 or making group of 2, and we found that making groups of 1s or 2s are more complicated than making a large group of 4, right? So if you do your cardinal map and you make the largest groups possible, what you're going to end up with is the minimal solution, right? Okay.
Sure, but there's not any method, sir. Like we supposed to group the highest amount
Yeah, but
before any other. Yeah.
Yeah, but there are sometimes design considerations, right? That for some reason you might want a slightly different circuit.
Oh, so you can manipulate it. Okay, sir.
Yeah. Yeah. But like, let's say I ask specifically for the minimal, right? The minimal SOP expression. What that means is the simplest one, like the one that uses the least amount of gates, right? If you can make one big group of 8, in a 8 in a sorry, a 3 input Carnot map, right? If you can make one big group of 8, right? And the answer is just 1, right? Because everything else is just 1, 1, 1, 1, 1, 1, 1. It doesn't matter whether the input in this is 1 and you make one big group, then the minimal SOP is just 1, right? If asked for the minimal SOP, that means I want you to make the biggest groups possible.
And sir, I didn't say include inside the slides, but would we have to convert the SOP and POS into the Karnaugh map?
How what?
Like convert it from, like how usually we do from Karnaugh map into the SOP or POS,
Yeah.
right? Do we
Yeah.
have to do? Would we have to do the reverse of that?
No, not for the test, but it's good to know for like
Okay,
if
had
you really
me
like
worried there,
digital
sir,
electronics.
because yeah,
Nah,
it was a bit
but
difficult.
it's kind of easy, right?
Sir,
Not-
sir,
Because you
we
just
would
think
have
of.
to like,
I'm sorry, you're breaking up.
sir, I was wondering, right, if we gotta work anything like moving from the minimal SOP to like standard SOP, or we won't be doing stuff like that.
No,
Okay.
because like it's not particularly useful right now. I kind of just want to test your Boolean algebraic skills, your Cardinal map skills, and your knowledge of theory.
All right, sir.
Yeah, so the multiple choice questions, right? Make sure you read the slides. The binary worksheet, right? The Boolean algebraic and Cardinal map worksheet, right? And all the stuff in the 7 slides, right? It's 7 PowerPoints, not a lot. Most of the PowerPoints is just a few slides, right? And a lot of the information is kind of redundant, right? So you see, we talk about parity checkers here. We also talked about this in chapter 1. So, some of the information repeats. All right, I'll type up
sir,
that email.
yeah. How long will the exam be?
2 hours, 2.5.
Okay.
Yeah.
All right. So Mr. Gill would be arranging the dates and so on, because you won't have to arrange that with us in terms of like clashes and so on.
So yeah, they should the HUD should arrange a timetable, because everyone's doing, pretty much the same courses. So they're gonna, 3 courses in the week in December and, the other 3 in the week in January, right? Or something like that. Maybe 4 and 2. And you should ask for a timetable if you don't have one. Right? But I doubt whether it's gonna be ready right away. Maybe next week you can go ahead and ask for a timetable, or Friday, and maybe you get it Monday. You can ask for a timetable. But there should be some sort of preliminary timetable that you can, look at and maybe come together as a class, say, hey, we want this electronics course exam. Maybe we change your mind. We don't want it, in January. We want it earlier, and we want mathematics in January. Mathematics might be a course is a bit harder to change the date, because it, civil as well as doing that, and mechanical engineer, so it might be harder. But maybe, telecoms, electronics, electrical machines, you can come together and be like, Miss Class, could you move this to January? I kind of want a little bit more time to study, or whoever teaching the course, right? Or Mr. Fraser, whoever, Now talk to them and move your courses around, suit yourself. All right, but you got to do it as a class and make sure everyone's aligned, right? When you ask, your HOD to move a course around, or your lecturer to move a course around. So that's why I usually just ask students, you want it in January or in December. Right? And I just put it there. I tell, Mr. Gill, the students say they would prefer it in January, so I go ahead and put that one in January. All right. Any other questions?
Sir, the date for the project, due date. I know you said the end of the semester, but any the specific date, sir?
Didn't I write it on? Pretty
Yeah, sure.
sure.
You put the date. You put the date in the document.
Yeah, you guys.
It's the date, sir. Yeah.
When is the date?
I think it's 17th.
Okay. The 17th of December. Yes. Is that sufficient? I think that's a lot of time for you, right? 17th. Okay. That is more than enough. Anything past that, you kind of be trying to do an assignment during Christmas. So do yourself a favor, finish it up before Christmas. Maybe a little bit of leeway I can accept up to the 23rd. I'm not gonna take out marks for that, but try to get it in by the 17th of December. If you push it to the 18th, still a little bit of grace period. I probably still gonna be busy marking the first 5 or 6 that come in. I'm not gonna reach yours as yet. So push it to maybe the 18th or the 19th. Okay.
All right, sir.
Okay. And I'm not gonna deduct marks if you submit, some lectures deduct marks if you submit like 1 minute past 12 of midnight in the midnight or something. Not gonna deduct marks for that, right? Just submit it around that time period. Okay. Good. Okay, good. So I'll send out an email with some tips for the test. You guys, enjoy the rest of your night. Any questions?
Sure,
email me.
Don't
If
forget the
I don't
recordings,
reply.
sir.
I'm sorry, what?
The recordings.
Yeah, I'll go look for them now. All right. Good. Any questions?
You'll update us on class for Wednesday.
No, there will be no class Wednesday.
Sure, thanks.
I'll send the recordings Wednesday. You guys can use to look at the recordings, I guess.
All right, sir.
Yeah. All right. Enjoy the rest of the night, guys. Bye.